So some of this is review. I would say the things that probably don't look like review are like this one and this one. Leading coefficient test and intermediate value theorem. Transformations means, we already did that, right? Transformations means how do you shift the graph by adding or subtracting, multiplying, putting a negative in front, inside, all that stuff. Finding real zeros, we've already been finding zeros. So we'll see what these two mean. So here's the graphs of polynomial functions are smooth and continuous, like this graph here, right? It's smooth, meaning it's smooth means it's not like an absolute value v. That's not smooth. It's got a sharp corner on it. Right? So this is not smooth. And by continuous, you mean you could draw the whole thing without picking up your pen once, right? Like that, but not like this, right? This, what does this remind you of? Piecewise defined function, right? So if you go up like that, stop, pick it up somewhere else, that's not continuous. Not continuous. These are both smooth and continuous. This is what the polynomial function looks like. Good. Kyrie? Naya, you okay? A lot of this comes, as you can see, I just copied it from the book because they've got good graphics and I can make it up. But some of this is not. Just remind yourself the basic shapes of polynomial functions depend on the degree of the function. What do we mean by the degree of a polynomial function? How many x's? The highest power term, right? Whatever is the degree, the exponent of the highest degree, highest power term, that's what the degree is. So remember, a degree equals 1 means linear, right? And that's the shape. A degree equals 2 is quadratic, and that's the shape. Degree equals 3, right? It starts to get more complex. With every degree you add, you get a little more complex. I was actually playing with this before, but watch this. So you could take something like this. Oh, I can go like that. Come on. Right. And I can move it down there. Right. How many zeros is that going to have? 1. Is there any way for it not to have a 0? A straight line like that? Unless it was horizontal, it's got to have a 0, right? How about this one? How many zeros could it have? 2, or it could have none, or it could have 1, right? And notice that it turns once, which in the vocabulary of the last chapter, we would call this point minimum, right? Even a relative minimum, but it's really the minimum of that graph. How about this one? Come on. There we go. So this one could have up to how many zeros? 3. But it doesn't have to, right? What if it had that? It would only have 1. Is there any way for it not to have a 0? No, because it's, going down infinitely that way and infinitely up. It's got to have 1 anyways. And we know the imaginary zeros occur in pairs. How many relative maximum and minimum points does it have? 2, right? It has and this is definitely relative, right? It's not absolute. That point is not the absolute maximum, because that's probably over here somewhere. But it is the relative maximum, right? And that's the relative minimum. Okay, let's try this one. So this is a quartic. Degree is 4. So how many zeros? But it doesn't have to, right? It could have just 2, or it could have none, right? And how many turning points are relative minimum and maximum? 3. So what do you predict for the degree equals 5? How many zeros will it have? Up to, right? So for degree 5, it can have up to 5 zeros, right? There would be 5 zeros. 1, 2, 3, 4, 5. It doesn't have to, right? It could be a little bit different than that. It's definitely going to have 1. Has to have 1. And how many relative maximum and minimum? I mean, as drawn, it has 4. So these are the rules, right? The number of real zeros have to be less than or equal to the degree, right? These two match. Right? And the number of relative maximum or minimum, which I do think sometimes in the book they call it turning points, which is fine, but we probably ought to use the vocabulary that we already learned. That could only be 4. So the general formula for this is the degree is equal to the maximum number of real zeros. The relative maximum minimum is always 1 less than the degree, right? For a 5th degree, you could have 4 turning points, or relative maximum or minimum. We good? Okay. But don't have to have that many turning points in them. This is an example of a 5th degree polynomial, right? This is negative x to the 5th. And how many turning points do you see there? You probably would count it as 2, like 1 there and 1 there. We don't have all of them. And that's expected. It's a less than or equal kind of thing. It's not absolute. And this is an x to the 4th. The x plus 1 means it's been shifted 1 to the left. But how many turning points does that have? It just has the 1, right? So the shapes of the graph, you can't always say, oh, cubic, that means this. It doesn't always. The one thing you could say for sure is that it has to have 1 less. It can't have the equal as the degree or more. The number of that many. Yeah. 5. This is the degree. 5. This is the degree. 4. Right? Whatever is the highest power. Okay, Morgan? In the book on this example, they actually say sketch the graph. And I don't want to sketch the graphs. I just want to say let's try to understand the transformations that go on, because we've already done this. It's really just a review. For example, this is an x to the 4th graph, right? So it could look anywhere like that, or it could look like that. But how is it being shifted? Left 5, right? That is a left 5. Right. Here's another x to the 4th. How is the graph being shifted because of this minus 7 at the end? Down 7. what two things are going on in this one? Yeah, this 7 is a plus, right? So it's up 7. And that, because it's got a minus in front, means it'll open down, right? So this is up 7, opens down. And what's going on in the last one? Okay, good. So the 1/4 multiplying means shrink. Shrink by a factor of a 4th, right? And then brought the -3 inside. Right 3. So none of that's really new. You know, most of the rest of this section is about graphing these polynomial functions, not by doing transformations. So that's what we keep the focus on. The first thing, this first objective, which I said was probably not familiar to you, is called leading coefficient test. Right? Leading coefficient test. And it's based on the definition of a polynomial function, right? A definition of a polynomial function, there's no parentheses. It has the highest degree term on the left, descending order of power, right? Every term might have a coefficient in front of it. So that first term, that's the highest degree term, and it might have a coefficient that's multiplying it right there. The leading coefficient term test, you only look at that term. You don't care about any of the rest of it. None of this makes any difference at all, right? You don't care. And this is how it works. When the highest degree is odd, it's an odd number, then we know that the graph, I mean, remember, odd number means like linear or cubic, right? Linear goes like this. Cubic goes like that. Actually, we even showed the 5th degree went like that. Every one of those, you know, it's either going to start negative and end positive, or if it was like a negative slope, it would start positive and end negative, right? So if n is odd, 1, 3, 5, 7, 9, doesn't matter what. We know that it either starts negative and ends positive, or if the leading coefficient is negative, then it'll start positive and end negative. It's flipped. That's what it's saying underneath there. And now, notice the language, because when you do the book, when you read, do the homework problem, and you look in the back of the book, this is the way they say it. If the leading coefficient is positive and n is odd, then the graph falls to the left, right? So if you're looking at it there, it's falling to the left, and it rises to the right, right? So it falls to the left, rises to the right. If the leading coefficient is negative, then it rises to the left and it falls to the right. Right? That's the language you're going to use. You know, and you saw a little bit of this in Algebra 2. Since they revised the SOL, they would be talking sometimes about end behavior of a graph. Okay, well, that's end behavior of the graph. What's the graph doing as x approaches infinity? It's approaching infinity, positive infinity. What's the graph doing as x approaches negative infinity? It's approaching negative infinity. Right, so these are the two scenarios when n is odd. Right? When n is even, are we good here? Yeah. Okay, Kay. Andy, you okay? Okay. When n is even, right, this is then if the a is greater than 0, the leading coefficient, that one right there, then it should start high, positive, and, it goes through up to 3 turns, but that leaves it going back in the same direction it came from. I mean, the two that we looked at were a parabola, right? That was 2nd degree, and 4th degree. In both of them, it started in a positive territory, made 3 turns, went back the same direction. Or it started in positive territory, made 1 turn, back in the same direction. And again, how would they word that? They would say rises to the left, rises to the right. The graph's going up. If you had a less than 0, falls to the left, falls to the right. Doing the same thing. Right? The end behavior, the way this one is drawn, as x approaches infinity, the function approaches positive infinity. As x approaches negative infinity, the function approaches positive infinity. Right? This one, x approaches infinity, function approaches negative infinity. X approaches negative infinity, graph approaches negative infinity. These are just that's the vocabulary of this stuff. There will be, I don't know how many, 6, 7, 8 homework problems about this. Your answer is going to be falls to the left, rise to the right, that kind of thing. You're not doing any calculations. You're just looking at that one thing. Are we good? Good. Right here, these are 3 examples. Right. So, negative x to the third plus 4x. N is even or odd. N is odd, and a is negative. Okay. N is odd, a is negative. So what will it be doing? To the left or to the right? Okay, just think of it. I mean, it's a cubic. So honestly, cubics we should kind of have in our head anyways. A cubic is generally this kind of shape. But since a is negative, it'll be this kind of shape, right? Rises to the left, falls to the right. Now you can go back at those last 2 slides and read it that way, but you ought to be able to make sense of it. It does make sense. Rises to the left, falls to the right. All right, how about the next one? N is even, and a is positive, right? So what will it do? Yeah, rise to the left, rises to the right. Again, it's a 4th degree, so we kind of know the shape of it, but we don't have to have 4th degree. If it said x to the 100th, you could just go ahead and draw yourself a 4th degree or a parabola and use that. It's going to be the same. And even is the same, no matter what it is. I should put that on the test, x to the 100th. Okay, so it's going to look like that, right? So that'll be, and they're probably going to say it like this: rises to the left and right. And how about the last one? N is odd, and a is positive. So this one will, this was odd and negative, and it rises to the left, falls to the right. This one will be the reverse, right? It'll be falls to the left and rises to the right. So if you're getting this, those homework problems are going to be like instantaneous kind of thing. If you're not, think harder. You can get it. It's not that complicated. Okay, the zeros of a polynomial function. And some of this we've already seen. There's not a lot of problems that are dealing with this exactly, but basically just making the point. If x equals a is a 0, then you say that x equals a is a solution of the equation, right? A 0 of a function, a solution of an equation. You know, the difference being like this, right? If you have f of x equals some function, let's just say x squared plus 5x plus 4, right? Then we would factor x plus 4 times x plus 1 and x minus 4, x equals -4 and -1. Those are the zeros, right? That's what makes the function equal 0. In terms of the equation, 0 equals x squared plus 5x plus 4, meaning there's no f of x. It's just the equation to solve. You call them solutions, and there's actually another word, which they didn't bring up here, but you've probably heard before, roots. The roots of the equation are the zeros of the function. Same thing. So the solution could also be called roots. And if the 0 is a, then x minus a is a linear factor, right? Because what is it that makes, what would you substitute for x to make that factor equal 0? A, right? That's why a is the 0, because when you plug it in there, you get 0. And then that point is also an x-intercept, right? The zeros, solutions, roots, x-intercepts, all the same thing. Ariana, you okay? Sorry. Okay. Find all the real zeros and then determine the maximum number of turning points. Well, what's the degree? It's 3. So what are the maximum number of turning points or relative minimum maximum? Just 2. I mean, that's the easy part, right? Turning points are less than or equal to 2. So that we don't have to do a separate thing. Find the zeros, meaning set it equal to 0. We've been doing this already. X to the third minus 12x squared plus 36x. Right. So what are our methods that we could use to find the zeros? Factor and graph. I mean, both. Since we're looking for real zeros, right? We're not interested in the ones that lead to the square root of a negative number or the imaginary, right? If it's a real zero, it'll show up on the x-axis. So either factor or graph. If you graph and it's not like an integer value that shows right up in your table of values, then you better know how to use that second calc 2 for 0, left bound, right bound guess, that kind of thing. But this one is clearly one that they would expect you're going to factor. 0 equals x times x squared minus 12x plus 36. And then what's inside there, that's a quadratic you could factor. Michaela? How's the factor? X minus 6 times x minus 6. So this is x times x minus 6 squared. So what does x equal? 0 and 6. Those are all the real zeros. Now, there is a fact, something that I think it's on the next slide. But, we expect that there's 3 solutions here. Yes? Remember, there's the number of turning points is 1 less than the degree. So that's 3, so it has to be less than or equal to 2. There's actually 3 zeros here, right? 2 of them are the same. 6, 6, 0. And we'll see in a minute how that works out. Good, good. Right. So when you have a repeated zero, like we did on the last slide, then that's called multiplicity, right? And I made another one up here. X plus 1 times x minus 1 squared, right? I mean, I just made it up and drew kind of a general graph, kind of using leading coefficient test. You know, I can tell this have a 0 at -1 and 1. The highest degree term will be x to the third, so it should have this kind of a shape. The leading coefficient would have been 1, so it's positive. So it should look something like that. But notice the difference in the graph at the two different zeros. At x equals -1, the graph goes right through the x-axis, right? But at x equals +1, it actually touches the x-axis, and then it goes back in the same direction. Right? And the reason is because that's being raised to an even power, it doesn't change sign, right, on either side of 1, because it, you know, whether it's a little less than 1 or a little more than 1, when you square it, it's positive, right? So it's not changing sign. That's what you look for on the graph to find a multiplicity that's, in this case, it's 2, but even. An even multiplicity means it does not change sign once it hits the axis. An odd multiplicity, which could be 1, it could be 3, it could be 5, then the graph goes right through the x-axis because it will change sign after it hits the 0, right? When you raise a number, a negative number to an odd power, you get a negative number. So what does this say? That's basically what they're saying there. So recognize that kind of feature. Okay. You know, I think we did a little bit of this in Algebra 2. You know, the common mistake would be like you say, find the zeros and state the multiplicity. And students say -1 and 1, multiplicity 2, but it wouldn't be clear like which 0 is multiplicity 2. It's not a general statement. It just applies to the 0, right? Not to the whole function. Good. Good. Okay, so there's going to be some homework, which is graph the polynomial function. And we don't just mean throw it in the calculator, but these are the steps that they're given to do it. The first step will be apply a leading coefficient test, right? Figure out whether it's falling to the left, rising to the left, falling to the right, rising to the right. Find the real zeros, which we just did. Right? Plot a few more points, and then sketch a smooth, continuous curve. So in this function here, right, 2x to the third minus 6x squared, the leading coefficient test would tell us what's the end behavior, what's it doing to the left? It's falling to the left, right? Since it's an odd degree and a positive coefficient, we would expect that it looks something like that, right? So I'll say, I'm going to draw an arrow over here. It's falling to the left, and it's rising to the right. Okay. Find the real zeros. Okay. 0 equals 2x to the third minus 6x squared. Factor. 0 equals 2x squared times x minus 3. X equals 0 and 3. Right, so let's put our zeros on the graph. Here and here. Right now, which one of those zeros is coming from a factor which has got a multiplicity which is even? Yeah, this 2x squared, right, that's the one. So we would expect on our graph, we should be getting something that looks like this, right? It'll go up, and then down, and then up like that, right? There's the multiplicity even. There's the multiplicity odd. But before we do that, let's plot a few points so we get a little more accurate. That's what they mean right there. Yeah?
So if the multiplicity is even, it ends on a, it's a vertex, and if it's odd, it doesn't.
Well, probably not. You would call it a vertex. You call it relative maximum or minimum. Yeah. Let me undo that. And we'll plot a few points here, right? The in this function right here. I mean, generally in this book, when they ask you to make a graph, and you put on the significant things that you can, like later in this chapter when we do rational functions, we'll put on that vertical asymptotes. And it'll say, then plot a point in between all those significant features and just past all the significant features. Like, maybe we should have 1 point in between these two zeros and 1 point here and 1 point here. So 3 points. So let's do that. Here's our table of values. X and Y. I'll do -1, 1, and 4. Okay, for -1, I'm going to get -1 to the third is -1. 2 times -1 is -2. And that'll be a -6, so it's -8. +1, 2 minus 6, -4. And 4. Right, that'll be 64, that's 128 minus 6 times 16, which is 96, so that's 2832. So that gives us a few more points to graph. -1, -8, 2, 3, 4, 5, 6, 7, 8. 1, -4, and 432, so that's like way off the graph right there. And so last step, sketch a curve. Make a smooth, continuous curve. Right, bounce. Something like that. Yeah. We solve right here. Right? What are the zeros? When it's in factored form, the zeros are 3, because that would make x minus 3 equals 0. Or 0, because if you plug in a 0 there, this whole thing equals 0. Right? We miss that one sometimes. Remember, a standalone x, not plus or minus anything, then 0 is the 0. Okay? Getting there. Ariana, you done? Angelina? Okay. Okay, try one more time. Now this one, the first is the leading coefficient test. So it's a degree is even and the coefficient is negative. What's the leading coefficient test tell you? Say again. Falls on both sides, right? I mean, just think, the most simple even degree function is a parabola, right? If it's got a negative in front, it opens down, falls to the left, falls to the right. So we can give this, it'll be an aid to our graphing, right? Solve for the zeros. 0 equals -1/4 x to the 4th plus 3/2 x to the 3rd minus 9/4 x squared. Now, first of all, I'm going to multiply through and get rid of these denominators because I don't really want to deal with the fractions. So what number will I multiply by? 4, right? The least common denominator between 2 and 4 is 4. So multiply both sides by 4. So 0 equals -x to the 4th plus 6x to the 3rd, right? Because the 2 goes into 4 twice, so 2 times 3 is 6. And then minus 9x squared. Okay, now looking at that, that's a pretty straightforward to factor that, right? What's the greatest common factor? There's an x squared, and you know what? I know I'm going to be leaving an x squared inside. I think I'll take out a negative x squared so that what's inside the quadratic is positive, is a leading positive. So let's make it like this. Negative x squared outside. That means inside I've got x squared minus 6x plus 9. And that's negative x squared times x minus 3 squared. What are the zeros? 0 and 3. Those are the same zeros we had last time, right? What's the difference this time? Yeah, they're both multiplicity 2. So I can put them on the graph right here and here. And we're expecting that it'll do something like this. It's going to come up, go like that, come up, go like that, right? That matches the leading coefficient test. It's doing the right thing at those even multiplicity zeros. Let's undo that. Okay, we need to do a table of values just to get those last few points. We should only maybe add 3, right? Something to the left, something in the middle, something to the right. And let's see. That's where it gets a little tricky. X and Y. So let's do negative 1, 1, and 4. Just trying to keep these numbers as small as possible. Let's see. Would it be okay if I plugged it in here? No. What adjustment would I have to make to my f of x values? I would have to divide them by 4, because I multiplied everything by 4, which is fine when I make a 0 there. It doesn't change the left-hand side. But if we're not at a 0 point, I can't just do that. So I could plug in here. I could even plug in here where it's already factored. It might be actually easier, and then just multiply everything by 4 that I get. Like, what if I plug in negative 1 here? The negative 1 squared is 1, and you got a negative 1, right? And then negative 1 minus 3 is negative 4. Negative 4 squared is 16. And then multiply by that, it's negative 16, right? But now I got to multiply that by 4, which is negative 64. Oops, that's a bad one. No, I got to divide everything by 4. Sorry. I think that's why he's staring at me with a quizzical look. Because I meant to say we need to divide everything by 4. We multiply by 4. Now we're going to divide by 4. And that'll give us, oops. Which is good. Okay, do the same thing with a 1, right? The 1, this first part will still be negative 1, but 1 minus 3 is negative 2. Negative 2 squared is 4. So that'll be negative 4 divided by 4, which is negative 1. And then 4 squared will give us negative 16 is the first. And 4 minus 3 is 1. 1 squared is 1. Divide by 4, negative 4. I mean, in the end, realistically, are you probably putting that in the calculator and just looking in the table of values? Yes, you probably are. But at that point, you're probably doing the whole graph that way too. So let me plot these 3 points. Negative 1, negative 4. 1, negative 1. And 4, negative 4. Right? And understanding the leading coefficient test, that means go something like that. So when you get to those problems, there'll be a few to sketch, right? He's supposed to be doing this stuff right there. And I didn't do their example. They have another example worked out where they're showing you step by step how to do that stuff. These are extras. In fact, they have 2 other examples where they've done it step by step. So you got to at least try that. And the last, I'm not even going to do an example of this. If you need more, look at their example. But this theorem will come up in calculus when you get to calculus. It's called intermediate value theorem. The intermediate value theorem, if you want to read the gobbledygook up here, what it's really saying is, if you're looking for the zeros of a function, and let's say you got your calculator set to only show you integer values of x, right? If you see a place where the y values change sign, there must be a 0 in between, right? It can't be negative at -2 and positive at negative -1, and somewhere in between -2 and -1 it didn't cross the x-axis. That's what the intermediate value theorem says. In fact, let me do this. Hopefully this thing is not. Almost there. Okay. Might be that. I don't think it's there. Next one. Okay. Use the intermediate value theorem to give, because it's every time you come back and say, I didn't understand what they're asking for, right? It says, to find intervals of 1 unit in length in which a polynomial function is guaranteed to have a 0. So for example, on this one here, I would say the interval of length 1 where this polynomial function is guaranteed to have is -2 to -1. Right? And I could use round parentheses because it's clearly not at -2 and -1, or else we would have seen it. That's the kind of answer you give for an intermediate value. They want to find the 1 unit interval, -2 to -1, or whatever it is, where you think there's a 0. Let's see if there's more. Okay. And that, honestly, I wouldn't worry about the rest of it. Just do that one part. Get the 1 unit interval. Okay, so that is the lesson. Okay. Right? We did our transformations. We at least described them. We learned a leading coefficient test. We found real zeros, and we sketched. And then intermediate value theorem we did at the end. That's the homework.